So you may want your green formula sheet handy just so you can see where they're going to show up. And when I said giving you some new equations, really, Jenna, we're going to derive them together based on the little game of catch that Connor and I just played. Okay. Momentum is the amount of motion an object has. If an object has more motion, it has more momentum. Really, the more momentum an object has, the less you'd prefer to be hit by it. So for each of the diagrams below, state whether the amount of motion is comparatively large or comparatively small. Here we have a tiny mass and a tiny velocity. Tiny mass, how about a ping pong ball? Tiny velocity, Connor and I playing catch. Did it have very much momentum? No. So we would say comparatively pretty small. What if we had a tiny mass moving really fast? Bullet. Small momentum or large momentum? What if we had a big mass not moving very fast, like a bowling ball or like that big weight that I had there? Well, you still really probably wouldn't want to get hit by it, so I'm going to say comparatively pretty large. Natasha, the worst ones are where you have a big mass and a big speed. As an example, dinosaur killing asteroid. That thing we figure had about the mass of a football stadium, and it was moving. Large is wrong, small is wrong. Massive momentum. World-changing momentum. World-changing damage. On a smaller scale, a locomotive going very fast. You may have seen videos, and when it hits something in movies, the bad guy classically is trapped in his car as the locomotive is bearing down, and you see the car hardly affects the momentum of the locomotive at all. Explain your answer? Well, momentum depends on mass and velocity. More mass, more momentum, more velocity, more momentum, more of both, way more momentum. What letter does momentum begin with? So we could use letter M from, oh, no we can't, because M was already taken. What does M stand for in physics as a variable? Mass. So here's what we do. Because momentum is a product, it's called the motion product, because you multiply to find momentum, we're going to use the letter P. And momentum is mass times velocity. That's on your formula sheet, I think, about 2/3 of the way down on the front page, I think, yes? What if you're going twice as fast? You got twice the momentum. What if you got twice the mass? You also have twice the momentum. What if you got twice of each? Well, now you got 4 times the momentum. It's going to do some damage. It is absolutely a vector. In fact, you'll notice I put vector arrows on the P and on the V. You're going to notice, Sydney, I'm going to start paying way more attention to vector notation in this unit. We kind of got sloppy in forces because we just said, oh, who's winning? Now we're probably going to fairly consistently let forward be positive and backwards be negative, or at least we have to be consistent throughout our whole question, because a lot of the questions are also going to ask you for a directional component. What would the units be for momentum? Well, what do I measure mass in? Kilograms. What do I measure velocity in? Momentum is measured in kilogram meters per second. I kind of like that because that contains the momentum equation sort of in it. Kilogram mass, meter per second velocity. And hopefully you have a physics teacher who's yelled at you and said it's worth memorizing units, because it is. I kind of don't like it because it's a bit of a mouthful. Kilogram per second. don't write this down. What were the units for force? Don't write this down. Except newtons was an abbreviation for mass times acceleration. A newton was really a kilogram meters per second squared, and they called it that for a while until they decided to name a kilogram meter per second squared a newton. Believe it or not, there is an international committee that decides these things. They are talking about renaming this an Einstein. It hasn't been done yet, but he doesn't have a unit named after him, and there is sentiment that suggests that he should. And since this has some speed in it, it'd be a good one to name after him. So in your lifetime, you may say that momentum is measured in Einsteins. I don't know. It hasn't happened yet, but they're talking about it. That's a little nerd trivia. I'm not going to ask you that on the test, which is why I said don't write that down. There's another way to measure momentum. Not only is it kilogram meters per second, it's a Newton second. In fact, another way to calculate momentum is to go force times time. Really? Yeah. Thomas looks skeptical. I'm going to give him a proof. Thomas, remember I said that Newton's was force, it was mass times velocity? Which means a Newton is a kilogram, sorry, I said mass times velocity, mass times acceleration. It's a kilogram meter per second squared. That's a Newton. So a Newton second would be a Newton times second. Thomas, my friend, is there an S on the top?
Yes.
Is there an S squared on the bottom?
Yes.
Well, holy smokes, Batman, one of those S's cancels, and I get kilogram meters per second. Momentum. Both are acceptable, Newton seconds or kilogram meters per second. I'll be honest, there are situations where it's preferred to write your answer and then use kilogram meters per second. There are situations where it's preferred to write your answer and use Newton seconds, and I'll be consistent with those situations, so I will flip-flop, and you'll figure out later on exactly when I flip-flop and when I don't. But for your purposes, Darcy, I won't take marks off as long as you use one of them. I don't care which. I've just introduced a new concept, momentum. Whenever I introduce a new concept, I kind of like to give you an idea of what's really big and what's really small. So example 1 says, estimate the momentum of a top pitcher's fastball. Estimate the momentum of a person and bicycle on a relaxed ride. Estimate the momentum of a car driving on a city street. I want to put it in some gruesome context. Instead of just estimating, I also want to estimate how much damage it would do if it hit you. And so I want to put this in kind of a basic context. If you got hit by a fastball, as long as it didn't hit you in the head, I think that would cause pain. But for example, if you got hit in the thigh by a pitcher's fastball, you'd have a bruise, but Natasha, I think half an hour later, you'd be walking, maybe with a bit of a limp and grimacing, but you'd be okay. As long as it didn't hit you in the head. If you were walking on a sidewalk and the bicycle and rider crashed into you, it might break a bone. It might send you to the hospital, but I don't think it would kill you. However, if you got hit by a car, what I really want to figure out is, okay, how much momentum can we absorb relatively easily? Owie, owie. How much can we absorb with injury? And how much do we just not want to absorb? Okay. What was our new equation for momentum? Momentum was equal to what times what? Mass times velocity. So, have I got any baseball players here? No one? Okay, so we'll have to best guess. Nobody plays baseball here? Wow, what an unathletic group. Anybody know the mass of a baseball? All right. Who has played baseball before? Raise your hand. All right. This is 1 kilogram. Hold it. Does a baseball weigh more or less than 1 kilogram?
Less.
Way less or a little bit less?
I'm going to say like
A lot less?
a lot less.
Okay.
This is pretty.
Here's half a kilogram.
I still feel like it's a lighter than that.
It is. Here's 100 grams, 0.1 kilograms.
Okay. It's like probably just
So instead of 0.1 grams, what do you think?
let's see.
Sure. So I said 0.1 grams, 0.1 kilograms, 0.2 kilograms, 200 grams, sure. You're not bad. By the way, none of you looked down at example 2 and noticed that I told you the mass down there? But okay. Close enough. Speed. I think it says top pitcher. I've watched American baseball on TV. Now we'll have to use miles per hour because that's the units they give us on American TV. What does the top major league pitcher peak out at? It's a nice round number. 100 miles an hour. I need that in meters per second. Thankfully, your physics teacher knows that to go from miles per hour to meters per second, you divide by 2 and then subtract a chunk. 100 divided by 2 is 50. Subtract a chunk. It's around 45 meters per second. How much momentum does a fastball have? Mass times velocity. Why are you saying no? 9. No. Okay. 9? You know what? What's a nice round number really close to 9? I'm going to say approximately 10. And what I'm going to argue is absorbing 10 kilogram meters per second. Ouch! Ay! Wow! But not much more than ouch, ow, wow. You might say some bad words. You'll hop around for a little bit. But probably a day or two later, you'll have totally forgotten. And even half an hour later, you might be fine. Oh, depends on where it hits you, but certainly if it hits you in a, thigh or kind of an area where you got more padding, you'd be fine. Bike and rider, estimate mass. Okay. How much does a bike and a rider weigh in kilograms? I know, so we're going to estimate. That's why I said estimate. Well, you know what? You guys aren't that familiar with kilograms because we still, in our system, tend to measure mass in pounds. So how many pounds would a bike and rider weigh? 200 pounds? Okay. So if you take 200 and you divide it by 2.2, that's roughly kilograms. Somebody.
90.9.
90.9? Let's call it an even 100, just as a nice round number because it's an estimate, and we'll say it's a football player in good shape or someone who's overweight riding the bike. Okay? So 100 kilograms approximately. Speed. How fast? And if you're not sure in meters per second, rough guess in kilometers per hour. I think it does say relaxed, yes? Does it say relaxed ride?
Yeah.
Okay, so we're not trying to catch up to cars or anything. So I doubt we'd even be going school zone speed.
15.
I've heard 30, I've heard 10, I've heard 15. You know what? I'm going to be really sneaky and compromise. I'm going to let it be 18 kilometers per hour, and you're going to see why in just a second. Because how do I go from kilometers per hour to meters per second? It's something to do with the 3.6, but I can't remember which one. Oh, you probably have that on the bottom of your formula sheet, huh? How many kilometers per hour is that? Ah, see how I managed to make it work out nice and even? Now, 5 meters, that's about the distance between me and Linnea. If you're riding relaxed, pedaling still, can you travel that distance in 1 second? You know what? That gut instinct seems okay to me. We might be off a little bit, but that doesn't seem like terribly off. Okay? We're not sprinting, trying to pedal as fast as we can. Yeah, I could pedal that and still be relaxed. So I think we're good with 5. How much momentum? Please don't reach for your calculator, Darcy. It's 100 times 5. Thank you. Car! Mass, roughly, guess. 2,000 pounds, divide that by 2.2. Divide that by 2.2.
909.
909,000 kilograms. Nice round number. Because cars have a big range of masses. Okay. Speed. I think it says on a city street, yes? So what's the speed on a city street? 50 or 60, depending on which street. Good. Divide that by 3.6. How many meters per second? 13, 14. You know what? Let's call it. It does say estimate and estimate, so I'm picking nice round numbers on purpose, because I'll bet you Darcy can do this one without a calculator too.
15,000.
Thank you. Basically, Darcy, if you're in double digits and you have to absorb that momentum, you'll probably be okay. No, double digits, 80, 70, 60, it's going to hurt. And it does depend on where it hits you. If it hits you right on the side of the head, that's a bad thing. But if it's hitting you like in your torso or on your legs, owie, 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 say some bad words, put some ice on, shut up and play. Probably. If you're taking 3 digits, 100, 200, 500, 900, 800, you're probably going to be going to the hospital. This would probably break a bone, depending on where it hit you, but probably. If you're in the thousands or tens of thousands, although I fibbed a bit, it's not just how much momentum you absorb, it's how fast you absorb it. Let's suppose, Connor, I was really mean, and I did throw this at you. Or I'm willing to bet you guys have done medicine ball drills playing basketball. What's the trick with the medicine ball when you're catching it? You absorb it. What you're really doing is you're increasing the time of collision. And that can lower the momentum. Sorry, I gotta be fussy. That can lower the force absorbed. By the way, that's why there is a time in another way to think about momentum. Okay? So I fibbed a bit. It's really not just how much momentum you're having to absorb, it's how fast you're absorbing that momentum. But all three of these are collisions where you're absorbing momentum kind of all at once. Although, again, a back catcher absorbs that all the time with their baseball glove, no problem. Piece of cake. No sweat. What does the baseball glove do? It's got padding. It lengthens the time of collision a little bit. So what can we do with some of this? Example 2, a baseball of mass 0.14. So you were, by the way, you were pretty good there, Haley. You were like, I think it's just slightly above 100 grams, above 0.1. I kind of talked you into the 0.2, but I don't even think you were quite heading there. I think at one point you were almost thinking like 150, which is really close to the actual mass. I was impressed. Haley, what does part A want me to find? Symbol for momentum is a letter P. Sorry, not an M, already taken. Momentum is mass times velocity. Tom, momentum is what times what, Thomas?
Mass times velocity.
Momentum is what times what, Connor?
Mass times velocity.
Momentum is what times what, Christina? That's going to come in handy. Do you need to memorize it? It's on your sheet. It's worth, in this unit, committing to memory because you're going to get sick of looking it up all the time. Haley, what's the mass? Yep. Be cautious. Once in a while, they'll give you the mass in grams. You have to convert it to kilograms. You have to convert it to kilograms. Kilo is 1,000. It's times by 1,000. Or sorry, divide by 1,000. Not times, divide by 1,000. What's the velocity? I can do this in my head. Because 14 is 2 times 7, 35 is 5 times 7. The 2 7 is going to be a 49 and a 10. 49, 4.9? 4.9? Yeah. 4.9. What? Units, please. Kilogram, meters per second. Hasn't been shortened yet. You could also have said Newton seconds, and I would take that. The fact that I use mass times velocity to find this answer, I would always write kilogram meters per second in my answer. But at Daniela, if you wrote Newton seconds, they're identical units. I'd take it. B. Tristan, what's B want me to find?
Velocity.
Velocity. Now, up until now, every time you've seen the word velocity, your brain has thought, well, VF equals VI plus AT. VF squared equals VI squared plus 2AD. And those still apply, but, you ready? What did we find, Tristan, in part A? But what word did we find in part A? Begins with the letter M. Momentum. What do they ask me to find in part B? You know, it'd be cool if there was an equation that had momentum and velocity in it. And there is. Right? Momentum is mass times velocity. What did you say they wanted me to find, Tristan? How would I get the V by itself? What will I do with that M? Oh, thank God. As always, Tristan, this equation, since it has 3 letters, is actually 3 different equations in one. Can I trust that you guys can rewrite anything to get it by? That's why I started this at the beginning of the year, knowing this was all coming. And by the way, now, when I see velocity, not only do I think, well, maybe they want VF equals VI plus AT, I also think, this one, how do I know which one to use? You saw exactly how I know which one to use. I went and looked at part A, and I said, what did they give me? So you're telling me another way to write velocity is momentum, is momentum divided by mass? You'd be right, sir. So it's going to be 4.9 divided by 7.26. Darcy, this one you're allowed to use your calculator for. Well, it's going to be a little more than 0.5? 0.675? Tristan, units, it's a velocity. Yeah, and I love the way you did. Oh, just a second. Yeah. This is also why I've said memorize your units and that you can take that part of your thinking out of the equation. Okay? What are we really saying here? We're saying, look, if you wanted this bowling ball to have the same velocity as the baseball, the bowling ball can be, the same momentum as the baseball. The bowling ball doesn't have to be going anywhere near as fast, and it'd be just as hard to catch. Oh, yeah, that makes sense. I've played catch with light objects and heavy objects. Semi-momentum is what times what? That's key concept number 1. Just as important, key concept number 2 is change in momentum. So example 3 says, prove that change in momentum equals mass times velocity change. We're going to do a proof. Okay. First of all, if I haven't done this with you already, and I think I have, but I haven't hyped it up, you should put a star next to this. This is going to become hugely important. Does anybody know, whenever I say change in, what's change in anything? What mathematical operation does it want me to do? More specific. What minus what? Nope. Close, though. Linnea, for a candy, what was that? Change in anything is always final minus initial. That's going to come in a bit handy this year. Any of you taking Physics 12 next year, this is worth memorizing. Next year I'll ask you to find the change in voltage. I'm really saying find the final voltage, find the initial voltage, and subtract them. Next year I'll be asking you to find the change in magnetic field. I'm really saying find the final magnetic field, find the initial magnetic field, and subtract them. Next year I'll ask you to find the change in momentum. I'm really saying find the final momentum and the initial momentum and subtract them. I'll ask you to find the change. I'll ask you to find a bunch of change-ins. And what drives me crazy is I'll say, find the change-in, and kids leave it blank because they don't know what to do. Where if I had said, could you please find the final thing and then find the initial thing and subtract them, they'd be fine. So it's worth memorizing. By the way, there's also a symbol for change-in. What's the symbol for change-in? A delta, which is a triangle, Greek letter delta, which is where we get our capital letter D from. Oh, really? Yeah. Just tilt the triangle on its side a bit, and there it is. What does it want me to prove? Ready? It wants me to prove that change in momentum equals, I'll put a question mark above the equal sign because I'm trying to prove it. I haven't proved that they're equal yet. Mass times change in velocity. I'm going to draw a little line down the middle of my page. I'm going to try and turn the left side into the right side. So Linnea, we're going to start with you. What's change in anything? So I can write delta P as P final minus P initial. Except instead of a P, I'm thinking the word momentum. Simi, momentum is what times what? So I guess final momentum would be mass times final velocity minus. Initial momentum would be mass times initial velocity. Yes? How many m's do I have on this side? 2. How many m's do I have on this side? You know, it'd be really cool if there's a grade 9 mathematical operation that I could pull in my back pocket and change this from 2 m's into 1 m. Really? So you're saying I can write this as m and then in brackets v final minus v initial? Patrick, v what minus v what? V what? Minus v. Did you say final minus initial? And what's final minus initial the same as? So are you saying that I could actually write this as m delta v? And wasn't that what I was trying to prove, that these were the same thing? So this gives us another equation. Change in momentum is mass times change in velocity is equal to, and then put a blank there. It's actually equal to something else. And we're going to combine 2 of these to find lots of missing stuff. So momentum, mass times velocity. Change in momentum, what's change in anything? Final minus initial. Change in momentum is so important, it has a special name. Can anybody guess what special name we give change in momentum? Impulse. If you're a Star Trek fan, you may have heard on Star Trek they talk about impulse engines. What they're really doing when they say use the impulse engines is they're saying change the Enterprise's momentum. They're not changing the Enterprise's mass, they must be changing its velocity. Impulse engines. They got the science term right. Impulse is defined as change in momentum. Mike, what's impulse defined as? Whenever I say impulse, what are you going to think? What's another word for impulse? What's change in anything? What's change in anything? No, what's change in anything? Okay, ready? Let's put the whole chain together. Ready, Mike? What's impulse defined as? Change in momentum. What's another word for impulse? And what's change in anything? So if I want to find the impulse, what am I really going to do? Final momentum minus initial momentum. Except there's another way to think about it as well. We can get the impulse equation. It says this. Fill in the steps below to find the impulse equation, the change in momentum equation. First it says take Newton's second law, F equals ma, and get the a by itself. Okay, Jenna, how would I get the a by itself in F equals ma? How do I move the m over? And you looked at me bored. I loved that. You were like, duh. So one way to write acceleration, Jenna, is force divided by mass. In fact, we just spent a whole unit doing that in all sorts of convoluted ways. Luke, there's another way to write acceleration from VF equals VI plus AT. Can you get the A by itself in the VF equals VI plus AT equation? Luke, what does this equation equal? What does the A stand for? Jenna, what does your equation equal? What does the A stand for? You're saying they both equal acceleration, then they both equal each other. And that's what I'm going to do in my next line. On my next line, I'm going to say, I guess that means that F over M equals VF minus VI over T. Patrick, by the way, can you read me, what does this say right here? Oh, he actually went even further. I thought I was going to get you to read final minus initial, and then I was going to say, what's final minus initial? And then you were going to say change in. You went right there. So I can actually, in the next line, I'm going to replace this with a change in velocity. In fact, let's do that right now. That's going to become a delta V And I'm going to cross-multiply to get rid of the fractions. By cross-multiplying, the m is going to end up right there. The f drops down like a domino, and there's a t next to it. This right-hand side is change in momentum. Another word for change in momentum is what? Begins with letter I. Impulse. This is momentum. Remember, I also said that momentum could be thought of as Newton seconds? Told you so. See it? Force times time. So, we get force times time equals impulse, change in momentum. And in fact, we get a 3-in-1 equation. First of all, here's what it's saying. On a basic level, if you want to change an object's momentum, if you want to make it speed up or slow down, if you want to change how much motion it has, the only way to do it is to push on it for some amount of time. To apply a force, an unbalanced force, for some amount of time. Believe it or not, isn't that actually Newton's first law? Because it's saying if you don't apply an unbalanced force, your momentum is not going to change. You're going to keep going in a straight line at a steady speed. Second, this also contains Newton's second law. How would I get the F by itself? I've lied to you. When I told you that Newton's second law was F equals ma, he never wrote it that way. He always wrote it F equals impulse over time. He was much more interested in that. So I wrote here, what this equation tells us is that a force acting for a time will change the amount of motion an object has. It must make it speed up or slow down. This is sort of a 3-in-1 equation. Force times time. Now on your formula sheet, I think I stuck a delta there, and that's because technically time is always a change in, and so it's traditional to write a delta there, even though at the beginning of the year when we did equations with time in them, we stopped putting the delta in out of laziness. This is equal to mass times velocity change, which is equal to impulse. The F should also have a vector on it. And what this also says is the direction of the change in velocity, that'll be the direction that you apply the force in. That's where your direction comes from. If you're pushing to the east, the direction of your impulse, your change in velocity, is to the east. Also, you can think of this as force times time equals m v final minus v initial, because that's really what those break down into, final minus initial, change it. So I wrote here, this is sort of a 3 equations in one, and it is. You can think of it as F delta T equals m v final minus m v initial. Where'd that come from, Mr. Dewick? I multiplied the m back into the bracket and FOILed it out. You can think of this as impulse, change in momentum, equals m v final minus m v initial. Darcy, I let these two equal each other. I let these two equal each other. And I guess I can let these two equal each other. Force times time is change in momentum. Oh, forgot the vector on the F. Is that on your formula sheet somewhere? I think the one in blue in the box here, all 3 stuck together. Yeah, I think? I don't remember whether I went F delta T equals delta P equals M delta V, or if it's there somewhere, about 2/3 of the way down, right? Yeah, you know what, I wrote it exactly that way. Oh, I put the F delta T on the right-hand side. Okay. Find it?
Yeah.
Connor, you good? Yep. Okay. You may have noticed I'm paying way more attention to vector notation than I've been doing in a while. Yeah. And this is because in momentum problems, there are often changes in direction because there's collisions. And when things collide, their direction changes. A baseball is pitched horizontally due east. You know what? The fact that they said due east, I'm going to put a little compass rose. As soon as they give me compass directions, I have a habit somewhere on my page, I'll put a little north, east, southwest. After it's hit by a bat, it moves horizontally due west at 55 meters per second. Kieran, what does A want me to find? Now, Kieran, I'm picking on you because you're a strong student. I'm hoping that you make a mistake, but every once in a while, it's a very subtle mistake. I also have a kid who sees it, so I'm curious to see which area you'll be in. Kieran, what does A want me to find? No? Oh, sorry, what? Say, yeah, what? Change of momentum. I was going to say impulse, so the first thing that I write down is that, and then I say, there's two ways to find that. I can find it by going force times change in time, or I can find it by going mv final minus mv initial. I can do it by going change in velocity. Which one do I use? Look at the question. Did they give me two velocities, or did they give me a force and a time? I'm going to use this one. And that's the procedure, Haley, always. Because it's three equations in one, and I only want to use two. Which two do I use? Well, impulse is change in momentum. And which of the other ones do I use? Go look and see what they gave you. So if you're okay with it, Kieran, it's going to be mv final minus mv initial. Yes? Cool. What's the mass? Cool. What's the final velocity? Direction? Okay. Minus, what's the mass? 0.144. What's the initial velocity? 38 is wrong. I thought you might get it. Why negative 38? So did you say negative 38? You said negative 38? She did say that? Oh, you restored my faith in you. I'm sorry. I didn't hear the negative. I just heard the 38. Why negative, Kieran? There's a change in direction, and you decided to let west be positive. As soon as you committed to that, you're committed. In fact, I might even have done something like saying, okay, west is positive, east is negative for the rest of the question. Now, you could have decided to let east be positive, perfectly fine, west be negative. It just means wherever you get a negative answer, you'll think west. Wherever she gets a negative answer, she'll think east. Okay? So negative 38, is that what you said, Kier? Okay. Which is what? How much impulse did this bat deliver to the ball? What change in momentum did this baseball undergo? What do you get? Yeah. 13.4? Positive or negative? You got a positive? So what direction will I write afterwards? Well, okay. 13.4 kilogram meters per second. I'm going to erase this because I got to leave the room. West. Okay. Brian, if you had let east be positive and west be negative, you would have got negative 13.4 on your calculator, and then you would have still said, well, it's west. You get the same magnitude. He already has, thanks. B. B. Harge, what's B asking me to find? Average force. Am I going to go F equals... what did A ask me to find? You know, it'd be cool. It'd be cool if there was an equation that had impulse and force in it. I think it's this one. I probably could use V final and V initial and time and find the acceleration, and then I could go F equals ma. But the nice thing about this is I think the F is going to pop out of here with information I pretty much already have, because how would I get the F by itself? So you're telling me another equation for force is impulse over time. I chucked the delta in front of the time because time is always a change in and I get lazy that way. The impulse was 13.4. I'll use my answer button on my calculator. Was it exactly 13.4 or did you round off? Yeah, so keep that number on your calculator, use the answer button. Time. Yeah, read part B. 0.8 what? Look at the units. What does that lowercase m stand for as a metric prefix? Milli. Yes, milliseconds. That's 10 to the... Oh, you don't need to memorize it. I put it on your sheet. Green sheet. 10, little lowercase m is... Replace that with 10 to the... Is it -3? Oh, so 0.8 times 10 to the -3. How many newtons of force? You're going to get a pretty big answer. Although it's a baseball bat, maybe you should get a pretty big answer. You wouldn't want to get hit by a baseball bat. Okay. But by the way, in terms of numbers, this is a baseball coming in at about 90 miles an hour as a pitch, and it's leaving at over 100 miles an hour. This is a major league baseball player swinging a baseball bat. So I think you get something pretty big here. What'd you get?
16,740.
So did you use the 13.4 or did you use your answer button? Yeah, it's 16,740. I'll go 16,700 newtons. Did you get a positive answer or a negative answer? So if we wanted to say what direction the force was, what direction would this force be in? If I'd asked that. West. Taylor, what's C asking me to find? Yeah. By the way, for both of these, the reason I said average acceleration and the reason I said average force, I don't know if you've ever watched a baseball in super slow motion when it gets hit by a bat. I've seen it. It kind of deforms and almost molds itself to the bat, and then it jiggles for like a couple of milliseconds, and then it rebounds. I don't think the force is constant, Taylor, and so I don't think the acceleration is constant. So as a nerd, I'm hedging my bets by putting the word average in front of it, but you can chuck the word average and just say, what did they ask me to find? Acceleration. What did I find in part B? Is there an equation that has force and acceleration in it? F equals ma. Can you get the a by itself, please, for me, Taylor? Yep. Which F? I'm going to write 16,700. You'll use your answer button. Which mass? 0.144. I could also have found the acceleration by going VF minus VI over T. That's also all in the equation, and that will also give me the same answer. This is a little cleaner because I'm using stuff that I kind of already know and have sitting on my calculator. You're going to get a big acceleration. Wait a minute. It should be big. It's a baseball turning around in a very short time. What do you get? Something in the 100,000s, I believe. 460,000? Is that right? No, I remember it starting with a 16,700 divided by 0.144? 116, and I'll go to 3 sig figs of 116 and 3 zeros. Is that what you said?
Yeah.
Oh, I thought you said 400 something.
No, 160.
Oh, I couldn't hear you. Meters per second squared. Did we get a positive answer or a negative answer? So what direction would you say that was? There you go. If they had asked for a direction. This question, I wasn't quite sure. It's kind of vague. We didn't ask for a direction for acceleration in the last unit because often we had masses moving in different directions and it would have been confusing. Well, one's going up, one's going down. Which direction do you want? I don't know, I just wanted the magnitude. Here, we're back to 1. Okay. Questions you can do already. Eventually, you're going to be asked to do all the questions from the homework. So if you're a nerd and you want to get a head start, you can try and figure the rest out. But for now, you can already do question the first, question the second, question the third, question 4, question 5. You can do number 6. You can do number 7. You can do more than that if you want to, but for now, well, you know what? 11 you can totally do. You should be able to cleverly figure out 8, 9, and 10, but I haven't talked about it yet, so fair enough. But 11 just wants you to find the momentum. 12 just wants you to find the momentum. 13 is good. 14 is good. Yeah, we'll pause there. You'll eventually do all of these, and I'll be honest, if you don't get to 11, 12, 13, and 14, if you just want to get to 7 and stop because you like to do things in order, you can. It's only about 6 minutes left, but you can get them all done in class and have no homework for the long weekend if you hustle.